Post-quantum cryptography is a classical system to protect classical encryption systems. It gets the spotlight, but it's not a quantum technology. But interesting areas are, for example, material science. This is actually how it even started. Feynman had the idea in order to simulate quantum systems, we need a quantum computer because they essentially simulate themselves. If you think about material science, this could help us design new materials, maybe more sustainable materials, whether it's for superconductors, for better energy transmission, or lightweight composites for aerospace. The applications in simulating quantum systems are endless.
Welcome to AI Catch Up, the podcast catching up with the tech products that matter in the AI era.
Hi, Hila. It is my greatest pleasure to welcome you to AI Catch Up podcast. You're a very special person when it comes to quantum computing. We have seen that United Nations have decided that 2025 should be the year of quantum science and technology. Then recently we have had the releases of Google Willow chips, and then at least in my circle, we have started discussing quantum computing very, very actively. That is why I think that it is high time to discuss this also with you from a bit more of expert perspective, rather than us just thinking, what is exactly quantum computing and how will it work? Before we start, maybe you could also introduce yourself and also share with us how you have come to the point where you are now.
Thank you so much for having me on AI Catch Up. It's actually quite funny how I came to be a researcher in quantum computing. So I didn't plan this really. I actually wanted to be a surgeon. So that was my life's goal since I was like 10 years old. But after graduating high school and working in hospitals and almshouses, I realized that it was not for me. So I went in a whole different direction. I started to study computer science, and my focus area was actually AI. And then by coincidence, I did university internship, and my supervisor at the time actually suggested, hey, do you want to work on a project that actually combines AI and quantum computing? And I said, sure, why not? I wanted to learn something new. And this is how everything started.
And what is currently keeping you busy in your daily work at Siemens?
My work revolves around hardware, software, co-design in this field. So essentially, I focus on two critical questions. First, how should the ideal hardware in the future look like to tackle actual real world practical problems that we currently can't solve efficiently using classical methods? And second, how can we design and write algorithms today to make the most of the very limited quantum resources that we have, but at the same time lay the groundwork for algorithms that will thrive on fault tolerant and much better quantum systems in the future. So on a day-to-day basis, I spend a lot of time bridging the gap between the theory and also application. For example, I work on identifying the requirements for quantum hardware to ensure that it actually aligns with the demands of practical use cases. But it's also important to explore algorithmic strategies to optimize the performance despite the constraints that we have, for example, noise and very few qubits. I take a deep dive into current hardware technologies, and we have different providers, and each of them have different advantages and disadvantages as they harness different types of quantum systems, such as photons, trapped ions, superconducting qubits. We have this huge playground where you can try out many, many different things, and it's uncharted. But I had to learn that, even if you get a result that is not working out or it's not working at all, it still is a result in figuring this thing out.
I think I won't be the first person that is actually setting you the task of explaining me quantum computing like I'm 5. Shall we also try this and think about how the, let's say not the 5-year-old person, but maybe 15-year-old person should think about this in very, very simple terms?
A lot of people are confused as to what quantum computers are, and some think it's this magical box that will solve all computational problems that we have. And it's not true. And it will also not replace classical computers. I stumbled over this analogy a few years back that I really like. If you compare classical computers to quantum computers, it would be like comparing a candle to a light bulb, right? Both give light, but they use completely different technologies and they have a better use for different scenarios. And that's the same thing with classical computers. And it's because they have different characteristics. So classical computers use bits that are either 0 or 1. It would be like flipping a coin, right? You only care about whether it lands on heads or tails. Quantum computers use qubits, and the first characteristic that they have is superposition. That means that they can exist in a combination of 0 and 1 at the same time, as well as everything that's in between. So for example, if you would spin the coin on the table, it sort of is heads and tails and everything in between at the same time until you catch it. And then you have another property that's unique in quantum computers, which is interference. So you can imagine having a ball and you just drop it on a pound of water, right? And it creates this ripples. And there's two options that happen. When two waves meet, they can either reinforce each other to make a bigger wave or cancel each other out. So in quantum computers, we use interference to amplify the likelihood of the right answers while reducing the chance of wrong ones. And then we have entanglement, which is my favorite one. There's actually a very fun paper by Einstein, Podolsky, and Rosen. They called it spooky action at a distance. So if you have two qubits that interact with each other in the beginning, then you can separate them across any distance you like. And as soon as you look into one qubit, you automatically know the information that the other qubit contains. And this goes beyond space and time. It's at that instance. So you could like imagine if you have like two gloves, right? One for the left hand, one for the right hand. You send them across any distance you like. And if I look into the one glove, which is for the left hand, I right at this second know that the other glove is for the right hand. And then in the end, of course, we do want the result. So we can measure the qubit, which means we let the superposition collapse in a state, force it to choose either 0 or 1. And this is a probabilistic scenario where it will then go to the state that is more likely depending on all the calculations in between.
I think that the first time when you were explaining to me the superposition, when we are having 0 and 1 coming together into one piece, and also the idea of the coin, I was already thinking that this is a kind of simpler for me to understand, just because I was doing something rather stupid in my childhood. I hope that not many kids are doing that, and I hope that my audience will also not do that. But back then, when I was, 10, our very fun game was to put coins on the rails of the tram. And then the coins splashed in a way, right? It was kind of, like if I would imagine that right now, that the tram is actually coming on the coin on the side, then it is squeezing it. And then you, in the same time, have one side and another side. And that is why, for me, the idea of coin that is having both sides simultaneously is something that I could have imagined, because I have seen that when we were putting the coins under the trams. But when it comes to your first metaphor on having candle and light bulb, I think that it is also very important to understand the candle and light bulb from the perspective of, but we have classical computing and then we have quantum computing. So which one is candle, which one is light bulb, and what are the different functions that we have here?
I wouldn't say that one is the light bulb, one is the candle, because I think people would then put too much into it. As just because the light bulb came after the candle, I'm going to say let the quantum computer be the light bulb. But the use cases that make sense for either one are actually very, very different. And I think in the future, it will just be complement to classical computers, just like we have high performing computing centers, just like we have GPUs. So each of these computers can solve different problems better. And we need to find a way to integrate quantum computers into already existing classical systems to actually have the most benefit. So if I can give an example, quantum computers have limited resources, as we heard in the beginning. So they will likely not be very suitable to handle large amounts of data. But because they can be in multiple states at the same time, they're actually really good at searching complex and large data spaces for something very specific. So that makes them, for example, very suitable for sampling. So if we think about quantum machine learning, then you could have quantum computers and classical computers complement each other, where quantum computers could enhance the sampling of the process and allowing to search larger data spaces, and for that matter, maybe have more precise results, whereas the classical computer could process the large amounts of data that we need in order to train our neural network. So both have their function and both are necessary in order to solve the very complex problems that we have in the world.
You have now mentioned something very interesting, namely quantum machine learning. A lot of researchers currently start to think, well, transformers are there for some time. We have already thrown a lot of billions of money on that. Some researchers refer to the concept of plateau when it comes to bringing more and more efficiency in the models themselves. So my bet would be that we would start exploring different architectures and different approaches and not just extend the ones that we are currently having. And then when it comes to whether we will be using quantum computing for bringing and extending this, where do you see the both fields interacting? Will it be on some sort of level of, okay, I, as the operator of the whole system, will be switching based on the task that I'm having at hand, and that would be handled by some sort of kernel or some sort of operation that will be happening within the main unit of the device that I'm using? Or would you see that it is more on the hardware side? And again, you are one of the people that are having this very fancy computer very close to you and you're probably being able to touch it, you know? But then I'm curious whether you can imagine that the parts of the quantum computing chips would be the parts of the chips that we are currently using. Will it be that level of interaction? Will it be happening in the hardware level, or do you see it actually being within the software switches that are then probably targeting certain operations such as sampling?
I think there's multiple ways to actually solve these issues. Even today, when we write code, you can actually, as a software developer, decide what to calculate on a GPU, CPU, and optimize that process. But you can also make use of compilers that take that decision for you and optimize it the best way possible. One direction that I see this going a lot is that high performance computing centers actually have started to integrate quantum computers into their existing systems. I don't believe you need a quantum computer at home or integrated in your laptop. It's mainly for very, very specific tasks, right? And then what I believe the case will be is that in the faraway future, you don't need to have an exact knowledge of the hardware. You will formulate a problem and then you will have libraries and SDKs that will do the work of distributing the labor in the most optimized way. Of course, for very, very specific tasks that are not pre-programmed as a developer, if you have the knowledge, I think it's great because you can write better performing algorithms. But for most people, you do not have to have the knowledge on the hardware. You will just input your problem in an algorithm and the hardware itself, like the compiler, will make the distribution of the labor. Let's call it that.
Yeah. In the machine learning space, we currently see this trend that we currently use way more natural language rather than even writing code. That is why I'm curious whether you currently have also the switch in quantum world. Can you write to ChatGPT, please write me the script, and then it will kind of output something good?
Not really, because there is not a lot of data on quantum code yet. Not a lot of repositories have solved problems. I think if you take very known algorithms like Shor's algorithm, Grover's algorithm, or QA/OA, then of course ChatGPT could implement it, but something that's tailored to the problem that you want to solve, that doesn't work very well yet. And what we also have to understand is if I have a problem, I cannot directly just send it to the quantum computer in its, let's say, classical problem formulation. I have to reformulate my problem in a way that is readable to a quantum computer. While there are lots of efforts into writing compilers that do automate this process, we're not there yet. We're actually still working on finding the best and optimal way to do that. So as for now, if you are a developer in the field of quantum computing, in order to write algorithms that really make the most of the very, very limited resources, you have to be aware of the hardware you're using. You have to be aware of its advantages, the qubits, even the topology of your qubits on the chip, and the noise levels you have, and how you can actually map your problem on the chip in a way that makes sense. So it is not there yet. But of course, I believe once we have fault tolerant hardware, for example, where you don't have the issue of how to map your problem in a way that you use the best qubits, the best working qubits, or if we have many, many qubits where it doesn't matter if you need 10 qubits more or less, then it will be the exact same way, and we will move towards low code and not having to know anything about the system. But not today. Today you have to know a lot about the hardware that you're using if you want to have reasonable results, right?
And I hope that everyone does. Something that I have not once heard as the main challenge to wider adoption of quantum computing is actually error correction. At the same time, to me, it is still not clear why the challenge is present. What is error correction about, and how we might approach this?
To give a little bit of insight why we have errors and why it's so much more difficult to correct those. We work with qubits, and some qubits have less error, other qubits have more error. And the challenge here is that you get your qubit in superposition. Once you measure the qubit, it can never go back to the exact same superposition as it has been before. So you cannot redo the exact same process because it's probabilistic. The second problem that you have is you cannot copy quantum states. We cannot copy the same states multiple times, have it calculated, and then just take the results that most likely. So we cannot take error correction methods that we have in classical computing and apply it directly to quantum computers. Other thing is, those little qubits are very dainty. They're very hard to control and they're very hard to put in order. Again, depending on the hardware, it's easier or more difficult, but generally speaking, they're very difficult to control, and applying gates to them or operations to them is not as easy. And in order to do error correction, we would need many, many more qubits that we can access right now. Because also having a chip that holds a lot of qubits is another challenge. It's growing every year, the number of qubits that we can access per hardware, and it's improving and improving. But we don't have the amount of qubits yet to do error correction methods that have been thought of by scientists that work in that field. The current approach right now is to focus on practical applications that can also work with imperfect quantum systems. So we're currently in the NISQ era, which is called noisy intermediate scale quantum. And with these systems, they're far from perfect, but they still have the potential to solve certain problems faster or more efficient. For example, optimization problems where you just need to approximate a optimal solution. And we can also write algorithms in a way that they are more prone to error and can handle error better. But we also think about pursuing applications that will be very useful once we have fault-tolerant computers, when we have enough qubits to actually do error correction. And there has been like an article by Google recently that they do have their first prototype of error-corrected quantum computer. So it is possible, physically speaking, it's possible, but it is still like very few qubits yet. But we're heading in the direction of having error correction in our systems.
I think that I'm finally getting it, why actually cryptography is the field where quantum computing is getting wide adoption. Because the system itself understands where the duplicates are between the states, and then it reduces the chance of them to appear. That is something that wasn't that 100% clear to me before. But then what I'm trying currently to understand as well is how exactly more qubits are helping us to solve the errors. Is it the number of them?
So we have physical qubits, the qubits that you have in your system, and you have logical qubits. And indeed, you need multiple physical qubits in order to have one error-corrected qubit. And you replicate the operation that you want to do on the one qubit very often. And then you will have some qubits that do what you expect them to do, and you have some qubits that do something else. And because the error rate is very high, you need a lot of qubits to do the same operation at the same time in order to determine the correct answer. But because we have very limited qubit and already problems need a lot of qubits to do the circuit itself, you cannot replicate it too many times. And this is an issue. So that's why we need a lot more physical qubits for one logical qubit. With IBM, for example, we're in the thousands of qubits right now. Oftentimes you get the question, how many physical qubits do I need to error correct one qubit? So how many physical qubits do I need for one logical qubit? This question is very difficult to answer because depending on the hardware that you use, or depending on the physical quantum system your hardware uses, for example, you can have superconducting or you can have ion trap systems. A superconducting system has different error rates for different operations, and ion traps have different error rates. So with the ion trap systems, they usually have very, very low error rates. So you need less qubits to have one error corrected. Whereas with the superconducting qubits, you have higher error rates. So you would need more qubits to error correct one. But then it is very difficult to have a chip with thousands of ion bits, whereas it is easier, not very easy, but easier to have more qubits on a superconducting chip. So sometimes when people read IBM has a system with now over 1,000 qubits, and another company that uses a different basis has only 50 or 100 qubits, doesn't mean that the IBM hardware can do more. Because there is a lot of characteristics that come into play on how you can map your algorithm. So with maybe 50 ion qubits, you could do more than with 500 superconducting. But it's then very dependent on the problem that you have, which system makes more sense, because there's also different connectivity and many other factors that come into place, which makes it so interesting to figure out for what type of problem, which kind of hardware should I use, which is a big challenge that we're facing.
What domains or where do people work that should actually consider to start thinking whether they should use quantum computing? What can those areas be, in your opinion?
We've mentioned cryptography before, right? It gets the spotlight quite a lot because sometimes people are driven by fear, and we know that quantum computers could actually break RSA encryption. There are a lot of research teams that work on post-quantum cryptography, which is funny enough, not a quantum technology, because post-quantum cryptography is actually a classical system to protect classical encryption systems. It gets the spotlight, but it's actually not a quantum technology. But interesting areas are, for example, material science. This is actually how it even started. Feynman had the idea, okay, in order to simulate quantum systems, we need a quantum computer because they simulate themselves. So if you think about material science, this could help us design new materials, maybe more sustainable materials, whether it's for superconductors, for better energy transmission, or lightweight composites for aerospace. The applications and simulating quantum systems are endless.
Are material sciences actually applicable to quantum computing because you have different variables that you should be considering, because we are having different molecules and different elements that should be taken into account? Why exactly is it the field to apply quantum to?
Because molecules and atoms and essentially materials are quantum systems. Classical computers cannot compute specific molecules that well and also just represent molecules. They would need a lot of computing power. Whereas for quantum computers, it's very natural because qubits are a quantum system themselves. So they would have to simulate their own behavior. That's why it is very, very suitable to simulate molecules, to represent molecules, and to see how molecules would react with each other, and just simulate that behavior in order to understand if certain composites of different molecules would result in better materials for any quantum system there is, really.
Fascinating, and does make sense. But is it? So material science, something else?
Yes, actually, a different thing. Drug discovery is also very exciting. So again, it could help model molecular interactions more precisely. And this can help speed up the development of new drugs or even personalized medicine that you can simulate, tailored treatments based on complex genetic data because you can present it in the qubits. There's also classical success in that regard. For example, AlphaGo is very groundbreaking for protein structure predictions, but it's not sufficient for a comprehensive molecular modeling in all contexts, particularly in scenarios where quantum effects play a significant role. Because again, you have a quantum system that understands quantum effects because it has it itself. Then it is very well suited for applications in logistics, supply chain optimization, especially large-scale optimization problems. I said before that it is very suitable to do searches in very large spaces and complex spaces because it can be in multiple states at the same time. If we want to take a simpler problem, for example, the traveling salesman problem, which you find in supply chain very often. You have a salesman that visits multiple cities and you want to find the shortest path. It's actually a very complex problem in computer science. It's NP complete. So I'm taking the worst classical algorithm. It would be checking like each route one after the other and then identifying which one is the shortest. We have much better algorithms there, but still not a very satisfying solution so far. With a quantum computer, you could actually check all the possible routes at once. If it's fault tolerant, of course. Right now, you do the same calculations multiple times to have your probability distribution. But in the future, you just do one swipe and you get the energy minimum, because in physics, nature always tends to seek the energy minimum. That's why a car rolls down the hill and not up the hill. So it's very well suited for optimization problems where you have infinitely many options for a few optimal solutions. Climate modeling is another area because climate systems are actually very, very complex, and we could do more accurate simulations to predict and mitigate the effects of what we're doing to a planet. There's actually a great project on that because we've destroyed a lot of coral reefs. It actually also killed sea life. We can do that classically to a certain extent now too, but we could do that even better. You could simulate where to add artificial coral reefs in order to help sea life to again start in those areas. So these are also ways of how we could help the environment. And on that note, it's not directly what we use quantum computers for, but because for those parallel computations, we don't need multiple classical chips like we need them now, we actually save energy. And then also quantum machine learning. It holds a lot of potential for transforming AI, but also AI can be used to help quantum algorithms. Fun fact, it goes both ways. Yeah, so cryptography is critical, but you can see many other fields where we can apply it, but not the one solution for everything.
I love how you are looking into very much real-world problems with quantum computing. Just very inspiring and fascinating, being very much on the breaking edge of everything that can be breaking edge. You're also very much into tangible and rather burning real-world problems. And what I'm curious about is how your background and how your process of growing up and also parents coming not from Germany, where you're currently based, has led to this point for you.
Thank you for that question. And for me personally, my background has had a significant impact on my approach to science, to problem solving, and also to life itself. I grew up as the child of immigrants, and I was actually deeply influenced by their resilience and also their adaptability. They've demonstrated it because they had to build a new life from scratch as adults, young adults, and it wasn't their choice. And their journey taught me that there is a huge value of perseverance and also creativity when you're faced with challenges. And I think these qualities are essential, if not at least very helpful in fields like quantum computing, where the path forward is actually uncharted and unknown. And this is the one aspect of it. And I was always hyper aware that the opportunities that we actually have in Germany, the accessibility to education, especially for women in science and technology or other fields, it's not something that we can take for granted. It's not a given, even though sometimes here it does feel like it. And this awareness has actually fueled my gratitude, but also always motivates me to make the most of everything that I get and the chances and the opportunities. And I value this freedom that I have. I can pursue cutting edge research, and I have a support system here that even if you're not privileged, you can achieve a lot. I'm not saying that everyone has equal opportunity, but you can still achieve so much. And I appreciate that. And that's why I always strive for excellence. And I want to create a contribution to solve problems that we have in the world. The research that I do, I'm not just doing it for myself. I do it for the people who cannot do it themselves. I always try to create work that other people can build on top of that might have less resources. And this is my approach to research and to life. And it is influenced by what I've seen and my parents and what they have told and explained. And I've traveled to Afghanistan too, so I've seen it firsthand, and I'm very grateful for everything that is possible.
With you being simultaneously a scientist and a researcher, but also, on the other hand, the big advocate of social responsibility and also of the access to technology, access to education, being given to people all over the world. What is actually your take on what we would think about the role of quantum computing in the society?
Yes, it's oftentimes overlooked, especially when we only think about progressing technology, especially when it's early stage. It does have the potential to transform society in a lot of ways. But with any powerful technology, you have responsibilities because you can use it for great things, but you could also use it for less great things. And one concern that's very immediate, which we have also in AI, is data security. So it could break our cryptographic systems that we rely on to protect us. And then beyond that, there's also an ethical dimension. We've seen it with AI, how bias and misuse can actually lead to significant harm. And we don't want to repeat those mistakes because at the same time, AI has also enabled us to do so much. Look up AI for good. I urge you to do that and to see how it has changed the lives of so many people for the better. It's incredible. But we should have started early on thinking the bias and how can we prevent that, right? So we will have the same thing with quantum computing. So we need to establish ethical guidelines and regulations early on. And we want to ensure that the technology serves the public good and protects the end user. And for that, transparency is key. As a researcher, I believe it is my responsibility to explain what we are doing, why we are doing it, and to make it understandable and accessible to everyone, and not just people that spend hours and hours every week on it. I want to demystify quantum computing and make sure that everyone feels included in the conversation and also confident to, in the future, use the technology responsibly. Quantum computing is a very collaborative research field, right? It brings together mathematicians, electrical engineers, physicists, quantum computer scientists, yeah? So it's not isolated. So it intersects with so many domains. That's why we need to share the knowledge and foster collaboration, because only together we can solve problems that we couldn't solve without each other. So we benefit from as many people as possible working on this together. I'm not building quantum computers, but to build quantum algorithms, but it's also to guide the development in a way that aligns with good values and use this for good and protect people that it impacts.
Is there actually some international system where one can see where each quantum computer is based?
The ones that are published, yes. So, for example, IBM, how many quantum computers they have, where they are based, how many qubits they have. Some companies are a bit more secretive about their hardware. Some people haven't published their hardware yet, and you cannot use them, but most companies actually do, and they're very proud. And in research, they want you to try their technology, because this is a give and take. Hardware providers also need to understand how they need to have their hardware built in order to solve problems. So they need the feedback of the users. And so it's a back and forth. So yeah, you can check out the companies that work on hardware. You can check out the companies that work on software. And yeah, you can get a broad overview on who is working on quantum technologies in general.
That would be probably the first step into the visibility of the topic.
Something to my fellow researchers is, for example, in our lab, when we publish paper, we actually also provide a reproduction package, which means that any other developer can just use the code as is without having to, with very detailed descriptions of what the code does. So other research can actually build on top of it, and you don't have to figure out the paper before. So it's great as a research community when we do research and we publish something to provide as much information as possible so other researchers don't have to do the exact same experiment again, but rather build on top of it. And you can do that with reproduction packages, Docker containers. There's so many ways to make it easy for other people to use what you have developed.
That is definitely not something that everyone is doing in the scientific field. And there is, a lot being said on the reproducibility. So before actually our listeners start clicking on the buttons to understand where exactly Hila's Docker images are, the question would be on where to find you if someone would like to contact you on the topics that we have discussed. What is the best way to reach out?
Right now it's LinkedIn. Feel free to drop a message and I will answer.
Thank you so much.
Thank you so much for having me. It was a lot of fun.
AI catch up brings the news. Tech solutions users can't refuse.